Yeah, let's start. The other people, if they join, it will be later. Yes, so I met, actually I didn't meet, I attended virtual WAS meeting, and I've heard Rebecca talk, which was very interesting, and I thought it will be very nice for her to present her work to our CHASC group. And Rebecca is a postdoc at University of Washington in Seattle right now, and she worked on Zwicky transient facility, so ZTF survey, and I guess also in X-rays. She did some X-ray work, working on XT and old variability data, and in optical on tests, etc. So I guess we can all listen to her work today, which will be on the recurrence analysis, and we can ask questions. Rebecca said that she can meet with people if there are questions and people want to talk to her. So you are free to contact her and chat this meeting. Okay.
Sorry, unmute myself. Let me get this into presentation mode. Can everyone see the screen?
Yes.
Okay.
Yes.
Sometimes it gets cut off, so perfect. Thank you for that intro. Oh, this is the very beginning of my talk. Give me 1 second, or the very end.
That's good to start. You start at the end and then
let's go in reverse. That'll be great. Get some time reversal going on. Okay.
That's your recurrence analysis on your own slides.
Yes.
Yeah.
Okay, there we go. Sorry about that. There. It was more or less the same thing at the beginning and the end. But yes, so I am a postdoc at University of Washington. I'll be presenting some work today that's kind of like a scatter shot of analysis I've done for a couple of different projects, but they all use methods from nonlinear dynamics. So I just wanted to give a shout out to some of my collaborators, which are Patty Boyd, Alan Smale, and Brian Powell at NASA Goddard, and Michael Vogel and Gordon Ridgers at Drexel, which is where I did my graduate work. And a lot of the material in this talk is from my dissertation, and then my PI is Eric Bellum from UW, and I'm just joining the ZTF collaboration with them there. So feel free to stop me, of course, at any time to ask questions. This is kind of a roadmap for where we're going to go. I'll give a little bit of motivation about why I'm doing nonlinear dynamics in astronomy, with really providing context with traditional time series analysis, but mostly just to provide a backdrop. I won't go into too much detail with other methods. But the main methods that I use are based on the phase space phase space embedding of time series. So I'll give a robust example for a neutron star before I really get into the meat of what's in my title, which is recurrence analysis, because really understanding phase space is how we understand the value of recurrence analysis. And then I'll go through some applications of that. So to get started, obligatory beautiful pictures. These are artist renditions. So on the left is as an X-ray binary where you have a black hole with an accretion disk getting matter from its stellar companion. And on the right would be a typical active galaxy, a supermassive black hole at the center of a galaxy, millions of solar masses, also with some kind of accretion disk. Now, there are, of course, now that we are able to take pictures of black holes, it's not the most helpful way or convenient way to get an idea of what's going on in the accretion specifically. And so we can look towards time series analysis, so light curves of these systems and how they change with time, and try and see if there's dynamical information in the light curves that can tell us something about what's going on in the accretion flow. These pictures are certainly beautiful, but the accretion disk can have many different geometric shapes. The accretion flow can be something like an advection dominated flow, which would be geometrically thick, but different opacity versus from the thin accretion disks or slim disks, where they're geometrically thin, but thick opacities. So these are the sorts of distinguishing things that we can't get from imaging that we're trying to get through time series. So I'm mostly interested in the long-term variability. That's on the order of like hundreds of days. So this is not necessarily probing timescales that are super close into the black hole, but more probing how the behavior, the global structure of the accretion flow changes with time on a very long-term time scale. And so on the left, it would be an X-ray binary in the X-ray observed by RXTE's all-sky monitor in the soft X-ray. And then on the right is around 3 years of Kepler monitoring of a Seyfert-1 galaxy. Beautiful precision from Kepler, which has given us some unprecedented data. And I don't know if I mentioned this, but the neutron star X-ray binary on the left was like 15 years long or so. So this is kind of the data that I'm starting with to try out some of my methods. So to give a backdrop of how these methods differ, I'll just talk briefly about time series analysis in general. So this is not an exhaustive list, I'll just say right up front, but let's say with frequency and time domain are certainly the most popular and definitely the first thing you do when you study time series. So that's something like the power spectrum or the autocorrelation function. So with active galaxies, for example, these are 4 active galaxies studied by Utley in 2002. And these are the power spectra, which shows that there's 2 slopes. And the frequency where that break happens between the 2 slopes has been found to scale with mass. Another example is statistical methods. So this would be like moving averages.
Can I ask a dumb question?
Sure.
Which has kind of always bothered me. I'm not an expert in this, in any of this AGN accretion disk physics. Why is it assumed that there is a break in the power law? I mean, why is it supposed to be a power law as opposed to a more smoothly varying bendy function?
Bending function, yeah. It's a simplistic. So this is more background. That's also my issue because I think it is a poor assumption when we assume a power law for the like a single slope power law as opposed to something that's bending. So there are more advanced modelings like in statistical methods or with karma modeling where that can accommodate bending slopes. This is 2 examples of 2 realizations from a karma model. The top is like a second order karma model where the 2 time scales are competitive enough that you get something that's kind of quasi-periodic versus a damped random walk, which would be basically a single slope, a power spectrum. But with both of these, and to your point, is there's some poor assumptions sometimes, or not appropriate assumptions that come into play. One being the break frequency doesn't show up everywhere in other bandwidths. Another is that this also requires assumptions about the time series being stationary, which anyone who's spent some time looking at active galaxies will come to find that that's probably not true all the time and a lot of the time. And there's just also a strong influence of noise where there's less confidence in some of these results. So the goal really is to connect like statistical features to intrinsic physical properties like black hole mass or the luminosity or something. But a lot of these challenges, like with the break frequency disappearing in other bandwidths, karma modeling requiring you assuming that the time series don't have any time reversal asymmetry, for example, those are some bigger problems, which is why I've moved towards, okay, what can we take from nonlinear dynamics that maybe doesn't have these kinds of assumptions? So that nonlinear dynamics is fundamentally based on the phase space, which is a dynamical kind of picture of the time series in like a higher dimensional space. And so this is stuff like Poincare plots. If anyone's studied any kind of chaos theory, that this is a Poincare section for a chaotic system where you have position versus velocity, which traces out this mathematical object called an attractor. So I'm going to get into what all this means and how it applies to astronomy imminently. So this is where we live. So the advantages of using these methods is that there's no assumption about whether the time series are stationary. In fact, these nonlinear dynamics, so nonlinear, can be applied to stochastic and deterministic time series, linear systems, nonlinear systems. So to give a kind of quick little physics 101 background on phase space, there's two, I adjusted the GIFs here so that hopefully it doesn't get too laggy on your screen, but what you're seeing are two like pendulums. On the left is one that's a simple harmonic oscillator, so it's just bobbing back and forth for all time, and on the right there's some damping term. And what's being plotted in traditional phase space is just position versus velocity. So the simple harmonic oscillator has a single ellipse here, so a single future for all time. So there's only one possible path, only one possible thing that can happen in the time series, versus the damped version has a spiral in towards the origin because position and velocity are slowing down for all time. And really, when we just look at the phase space, we can infer what's happening in the time series, like in the time series, the velocity or the position. And they are distinctly different geometric shapes in phase space, which is kind of the key feature that we're going to be working with. So for something that's a little more complicated, hopefully this will play. Yes, so this is the Doffing Oscillator. And so just the top left is just the potential rather than a swinging bob. And the bottom left is the time series slowly coming out and what it looks like in phase space. And we start to see kind of traces of similar behavior to the kind of a combination of effects from the other types of pendulum, where we don't exactly have a closed curve, but it's coming close. So it starts to almost repeats itself. Maybe it follows itself again for a little bit and then deviates. And what's being traced out in phase space is actually unique to the class of differential equations. So this is for the Duffing equation, which is this blurry equation here on the bottom. And this includes nonlinear terms, a driving term. But the key point here is that the structure, the topology in phase space is unique to this equation. So really these are the sorts of features that we want to be able to quantify in order to identify what's the underlying system. So one way to do this, so here on that title is phase space encodes dynamical information. So we can look just at the phase space to try and infer what's going on. And so as an example, this is the Duffing equation again, but it's just one solution and it's one coordinate on the left. So it's just some scalar time series. And I've highlighted I realize that there might be somebody who's colorblind, but that's red and blue on the left and then right segments of the time series. And if we were to embed it in phase space, and now we're talking 3 dimensions. So units aren't really a thing here because this is just a numerical solution to an equation, but this would be like x, y, or z, or flux in its first and second derivative. If we highlight these 2 trajectories, you see that they almost trace each other exactly. There's like slight deviations. And that's because these are what are called unstable periodic orbits. So in a like regular pendulum, where you had that like perfect ellipse, that is a stable orbit. It's a stable periodic orbit with a fixed period. Here, because there's this nonlinearity, there's inherent deviation in the equations. This unstable periodic orbit doesn't quite repeat itself, which is a little bit more representative of real systems. So one way we can like describe the geometry in phase space is by finding all of these unstable periodic orbits and seeing how they wind around each other. This is basically just like mapping out what the shape is from standing inside a house and like taking distances, basically taking a measuring stick and measuring each room from wherever you stand. And so you do this with.
Quick question.
Yeah.
So what is the third coordinate? I mean, I understand that R1 and R2 are X and X dot, right? Or...
Yeah. So in this case, this is differential phase space. So that just means the time series itself is R1. R2 would be the derivative of this. So this would be a numerical differentiation. And the third is that second derivative.
Oh, the second derivative. Okay.
Yes. And so you could keep going like 4-dimensional space, but I'll get into that later.
So one question
here.
Yeah, so if I look at this visualization in 3 dimensions and think about it, I mean, does it tell me anything if I just see the distance between one and the second one? I mean, what does it tell me about the differences between the red and blue parts of the light curve? Is it like just the same but shifted, or?
Yeah, so it's basically a section of the light curve that's almost repeating itself. And I will give a real example of this very thing with the neutron star X-ray binary to kind of show what this means. But if we were to try and see how similar or different they are, one of the metrics for determining that is called the relative rotation rates. That's basically how do these two, like if forward in time is kind of like your normal, how the two trajectories wind around forward in time around each other is going to be some number. It's going to be like blue curve rotates around red curve, once every 2 pi or something like that. And so you can do this for every pair of trajectories in phase space. This is the equation. If you're really interested, don't worry about it. I'm just describing it in words. But the main point here is the text, which says that the set of relative rotation rates, which is 3 R's, for the entire light curve, for the entire system, you go find each of them. It's going to be like a set of integers and fractions. And that's going to be unique to the differential equation. So the Duffing equation has a fixed set for something that lasts period 1, something that lasts period 2. The comparison of all of them are going to be fixed set of numbers. And that's based on the Berman-Williams theorem. So this, don't worry about the details so much. The main point is that there is some set of numbers that's specific to this system. And if you were to do the same thing on some other system, maybe some unknown system, and compute the relative rotation rates, if they're the same, then those two observations come from the same system, same underlying class of differential equations. So this is where the power is, because you can do the same thing for the neutron star X-ray binary. And I would preface this by saying we had evidence that this had nonlinearity in it before this analysis was done. And so that's going to be an important point later. But this is the light curve, and this is what it looks like in quote phase space, where I've just taken the first derivative of the flux, which is an interesting physical quantity to think about. But we see this kind of double weld behavior. There's 2 axes of rotation for this time series when we embed it. And so if we do the same thing, so this is just the 2D version, not 3D, but you highlight 2 segments of the light curve, which are almost repeating themselves. These would be period 2 segments of the light curve, and then calculate how these wind around each other with that integral I showed earlier. You calculate that for all the pairs of orbits. you assemble them into this nice little table and ask the question, does this look like the Duffing equation? And the answer is yes. And so that becomes a powerful tool of saying, okay, this light curve, weirdly, must be the underlying thing or like kind of mathematical object or attractor that generates the light curve is somehow related to the class of differential equations that the Duffing equation comes from.
Can I ask a quick question?
Yeah.
This is fascinating, but the part I don't quite understand yet. These differential equations, partial differential equations, they are deterministic equations, right? They're not stochastic.
Right.
So what they're calculating is kind of like a mean structure, expected structure. They're not exact. Every curve follow that equation, right? Because there's randomness going on. So right?
Yeah. Yeah. So the relative rotation rates aren't like exact. It accounts for the fact like how many times does it go around each other. This is obviously, you can see here that it's a little noisy and wiggly, but that's why it's a set of integers rather. So there's error here, a less than like plus or minus that one integer basically for each of these measurements. But to your point, this system is fantastically nonlinear. That's not the case generally. Most systems have a lot of stochastic noise in the light curve, so that it becomes less possible to do this kind of analysis.
I see. No, I understand that. So I guess I think my general question is there a stochastic version of these differential equations taking into account the noises instead of just treat that as approximately deterministic?
The differential equation, you mean the Duffing equation?
Is it possible to introduce some, stochastic component into, because there are stochastic differential, partial differential equations, right?
Right. Yeah. So in this case, we're talking about system. So that gets a little complicated in that the fundamental structure, like the relative rotation rates, can only be done on dynamical systems, so deterministic systems, where certainly the observations, you can apply it to experimental data, but it loses meaning if the thing you're comparing to doesn't have an attractor. So some kind of geometric, doesn't have any kind of like topology in phase space. And so I'm less familiar with stochastic differential equations. I feel like they're probably analogs to that. But this is the theorem that this is based on is specifically for like diffusive processes that are deterministic. I don't know if that answers your question.
No, that's fine. I was just thinking about how to add on
the noise.
Right, how to add on, whether add it into the system itself or treat this whatever solution here as like a statistician would think about. It's like the mean structure, expectations, then you on top of that you're adding noise. I don't know which way, but that's what I was thinking about. Yeah.
I think it would help. So this isn't where I'm going with this is going to be a method that does include stochastic considerations. So I think I'll continue and then we can circle back to that.
Charlie, quick interruption. So the power law thing that we're doing with the solar flares, I mean, I think it's dependent on a stochastic Langevin equation.
I see.
So they are essentially the noise term comes in through a standard normal error term, which when marginalized over turns the equation into into this beta what is that thing, the gamma distribution thing.
I see.
That you noticed before.
Sure. Okay. Thank you.
And I have a pair of contradictory questions actually, Rebecca, about the equations that you had before for the RRR.
Yeah.
I think it was on.
Do you want to go up?
Yes, please. Slide 16, I think. Yes. So
Here?
first of all, I don't understand what zero means in this thing? How does how do I interpret the value of zero as in how many times does it?
So this is comparing this specific trajectory to itself along the diagonal.
So
there's no rotation is what that means, because it's just comparing the exact trajectory to itself. This is just, I could have just left that blank, that diagonal.
Okay.
Yeah.
Okay, and so here's the contradictory part.
Yeah.
You have a delta R cross D delta R term in the numerator over there. So why is it anything but zero? Where does the non-zero part come from?
Sorry, in the equation?
Yeah.
Where
there's a delta R cross delta R.
Oh, I see. Yeah, so this is the derivative version. In practice, how you would calculate this is more a graphical way, where this projection here in phase space, you see how many times one curve folds over on top of the other, which is how you get this kind of integer number, versus these values, if I were to calculate it on pen and paper, for the Duffing equation would be possible because it's a differential equation that I can actually solve. But in order to compare to experimental data, we use kind of an analog to this integral through the actual graph here on the right. I didn't put a slide here of that process, but I can share that with you later. I'm sorry that was confusing.
No, so but then this equation must be there must be a modifying term somewhere.
Yes, yeah. Sorry about that.
All right. Okay.
This is like the theoretical version, but in practice it's slightly different in the code. So so really this kind of leads me into the next questions, which are how do we generate phase space for unknown systems or stochastic systems, because phase space of something that's like noise-like gets really messy. And then how do we automate the extraction of information in phase space? So this was the example I just gave, is not well automated. I have to sit there and look at the phase space and calculate rotation terms, which really is a lot of human involvement. And so my question is, really, how do we kind of take a step back and try and look at structure more generally or across an ensemble of time series? And so there's two methods I'm going to talk about. One is the time delay method. That is, how do we get a scalar time series into some kind of phase-based version for space, higher dimensional space. And then once we've done that, I'll introduce the recurrence plot, which is addresses a lot of kind of the questions that I think we're all having. And so quickly, time delay embedding, you can think of it as, I'm going to use the Rossler attractor here as an example. Let's just say that this is, quote, the real system or the theoretical system, and we can stick it in a black box. We don't know what it is. And all we get out of it is some scalar time series. So this is probably the x coordinate, I think. How do we get from just this information alone, how do we get into phase space? So what I'd shown previously was just taking a numerical derivative. That really only applies if you know the system is low dimensional or deterministic or nonlinear already. So the neutron star that I was just looking at, we had evidence that it was already low dimensional, had possible chaos. And so it was a good assumption to just use one or, embedding in phase space only up to like 2 or 3 dimensions. But when we talk about unknown systems or ones that are maybe stochastic in nature, we have to use different techniques. And so one of them is called the Dawkins transformation, which is basically you just take delayed copies of the time series and plot them against each other in order to get some kind of phase structure. So the best way I think about this is when you think of sine and cosine. When you offset sine by pi over 2, pi over 4, it's in phase. It like looks, or not in phase, it looks like its derivative. And so if you were to plot just in 2D sine versus some delayed copy of itself, for the right choice of t, so right choice of an offset, you would see it maximally unfolded. You'd see something like an ellipse or a circle in phase space for the right coordinate. So that is basically what we do here. And so this Hawkins theorem basically says for the right choice of a delay and the right number of coordinates, the number of times you do it, the number of dimensions that you use, you'll be able to recover the original system that generated the scalar time series. So for the Rossler, you know, embedding it in 3 dimensions with the right choice of this delay will give us the same structure as the original attractor that produced this time series. So that is the concept of time delay embedding, which is what I've used for all of my work from here on out. There are other types of methods for getting into phase space from a single time series, but I'm not going into them here. So the recurrence plot. Once you have some either theoretical system or experimental data that has some phase space, so X representing all of the coordinates in phase space, the recurrence plot is defined as comparing every position in phase space to each other. You take 2 points in time, represents 2 positions in phase space. You see how close they are to each other. So if they're within some threshold distance, then we insert a 1 into this 2D matrix and a 0 otherwise. And so in a nutshell, this just means you have a square 2D matrix. It's filled with zeros and ones. The ones are the positions everywhere in the matrix. So I and J are 2 points in time. If there's a 1, those 2 points in time are close to each other in phase space. And this can be visualized. Since we're talking about a binary matrix, you can make a plot of it and look at it. And so that's where we're going. Anyone have a question?
Yeah, there is a hand raised by Andrew.
Sorry, it was on the last slide. Can you clarify again why this time delay is better than just taking a numerical derivative? Like, I mean, I could just take n numerical derivatives, or I could take nt time delays. At least in the numerical derivative case, I know what I'm doing, rather than in this case, you have to pick what t is, and I'm just not sure how hard that is. So can you maybe say why this is a better idea?
Sure. So a couple things with that. One is you don't necessarily know whether the derivative, if we're an unknown system, the derivative might not be the right choice for maximally like unfolding the structure in phase space. So the point of getting it into phase space, if we're thinking back towards something that's like a deterministic system, we don't want different trajectories to cross paths, because that would basically be the same as having multiple solutions for a single point. So you want unique solutions to a differential equation. That's kind of like the theory side. But in practice, that just means we want it to be maximally like unfolded or ballooned up, so that as many paths are not crossing as possible on the one side. So a numerical derivative does not guarantee that is the case. And the other hand is when you take the derivative, you're increasing the noise. So if we're talking about experimental data, every time you take the derivative numerically, you are increasing the noise with each term. Whereas in the time delay, it's constant noise term, uncertainty terms for each dimension. So that's one advantage to it. You would have a hard time getting into higher dimensional spaces above like 2 or 3 using the derivatives, because then all of a sudden you get hugely dominated by noise.
And so maybe you're going to talk about this, but I mean, but you pay the cost of having to choose t and having to do some optimization over what that t is.
So t is, one of there are a variety of ways to choose t, like methods for doing that. One is to choose the autocorrelation time, because really what you want are if you're sampling points along the time series to produce a single point in phase space, you want each of those, each of the terms for this position to be uncorrelated to each other. So it would be redundant to take 3 points in time, like super close together, that you're basically representing the same state. And so you would get something like a diagonal, just like some long diagonal line in phase space, which doesn't give us any dynamical information. So one method is to use the autocorrelation time, or the first minimum in the mutual information is another way. Another is to just do it by eye. The most popular, I think, is definitely using something from the autocorrelation function.
Thanks.
Yeah. And then the same, there are methods for, how many dimensions do you use as well, which is the most popular, is called the false nearest neighbors method. Excuse me. So the recurrence plot, though, once we have something in phase space, the recurrence plot is actually pretty straightforward to calculate. You just take the distances between every pair of points, basically, and if that distance is less than some threshold, you have a 1 in the matrix. And you can visualize this. This is an example. These are 4 like kind of canonical type systems. White noise. So here, this is exactly the representation of the recurrence matrix, where each axis is time. And so where a position is on this plot tells us, if it's black dot, that tells us that those 2 positions are close to each other. The 2 positions in time are close to each other in phase space. And so for sinusoidals, it's 2 sine waves added together of different periods. You get a lot of diagonal lines because there's, and those are all kind of evenly spaced. It's because at those offsets from each other in time, you get something that's like in phase, basically. Logistic map with a drift, so this is non-stationary. You get kind of fading out in the corners, and Brownian motion. And I will get into the detail, but of how we quantify this. The big picture point is that you can right off the bat, just by looking, see that these systems are all different. They must, strongly diagonal lines is distinctly different from like randomly distributed points, which I can automatically, just by looking at the recurrence plot, say that's clearly a sine wave, and that's clearly white noise. It's not always this obvious. When we get into systems that only have slight differences, it's harder to see it, which is why we need methods to like quantify the structure going on here. These are some more examples. In this case, we have a distance plot, which would be like, I'm just checking the time. Distance plot, which would be removing the threshold. So instead of it being black and white, the color indicates how close they are in phase space. So this would be the example from the neutron star X-ray binary. Time series, let's just say we're using numerical derivative in this case, though you can also use the time delay embedding. And a black dot tells me, oh, 2 points in time are close to each other. So this, like, there's a string of trajectories kind of here that all pass through some like tube, basically. Each trajectory represents a different point in time. And so those pairs of times would just be the 2 positions in the recurrence plot. There is an analog to this with the autocorrelation function. Let's say I like scrapped the phase space. I didn't do any embedding. Instead, all I did was compare the time series to itself, to itself, to some delayed copy of itself. We get the same plot like this, but if I were to like collapse everything along the diagonal, I would get exactly the autocorrelation function. The difference with the recurrence plot in practice is that you first, rather than looking at like how different 2 points are in flux, I first projected into phase space. So this acts kind of like a filter, because anything that's like just 2 points that kind of show up next to each other merely because of happenstance, like a noise, if you embed it in phase space with the proper dimension, those very likely, may or may not actually show up next to each other, because when you start unfolding in phase space, you're approaching more of the deterministic structure that exists. in the light curve. And so these correlations have more to do with the dynamics rather than the noise. There are ways to actually quantify that as well. So these are classic 6 X-ray binaries. These were produced by first doing the time delay method for the phase space. And then this is just as an example of different types of features that you would see. You can't, because of the resolution, HERX1 has a pretty solid clock of 35 days. You can't really see it, but if I were to zoom in, you would see a bunch of diagonal lines all spaced by about 35 days. So it really it's really a good probe for periodicity. LMCX3, on the other hand, you don't get like these perfect diagonal lines. You instead get kind of diagonal structures. And that's because there's noise in the system, or that period wobbles more substantially. So this is also a good way for detecting kind of quasi-periodicity as well, or a drifting period or something. And that's all just qualitatively. That's if we're looking at it. So there are ways to also, I'm just going to pause here. Were there any questions about this so far?
I had a question to this previous plot with different sources, the previous slide. Yeah, here. So the the one with Cygnus X1, for example. Yeah, the data. Yeah, here. So in Cygnus X1, we see this blocks of points in recurrence plot. Is this because of the amount of data you have in the light curve, or is it really the intrinsic? How you have this? Here? Yeah, you have like this central clump with a lot of points.
Yeah. So yeah, I realize this is like kind of new for a lot of people, so I'm kind of flying through this. But when you create the recurrence plot, one of the first things you determine is what's the threshold. So how are you determining whether 2 points are close to each other in phase space? Like what threshold distance would indicate whether you plot a dot here or not? And so what this is showing is there's some fixed threshold for the entire light curve here. And in the middle of the light curve, so this is somewhere in the middle of the time series, or in the light curve, a lot of the points are kind of hanging out, or are very close to each other for in time, or in the phase space, excuse me. So that's
so this is in the but is this related to the sampling in your light curve at all or not?
Is this related to what?
To sampling, so the observation time bins.
It could be. So like, for example, so the repeating, so you get a lot of density here because the points are really close together. So yeah, but the sampling is constant through the entire light curve here. So it just so happens whatever the variability is going on at this point in the light curve is either, it could be like faster variability, so that whatever sampling I've chosen for the entire light curve, there's some new feature variability going on that's happening on faster timescales, perhaps. Or alternatively, it's just that for the segment of the light curve, you have, you're getting a point when 2 things are close to each other, but you would get really, really high density for like a sine wave as well, where the threshold is large enough, where it's just following each other for a long time. So this is like it's repeating itself probably at a really high frequency is how I would interpret that.
Okay. Yeah, because this one is very different than SMCX1, the one at the bottom, for example.
And this one is this is another neutron star XRB, is that right? Yeah, I think this one is similar to HERX1, where it has a pretty strong repeating period. So yeah, I mean, that kind of leads into how do we
question about the threshold.
Yes.
I mean, you mentioned that it's the same for the entire duration of the observation or something, right?
The threshold.
Yeah, meaning that the intensities at two different points should be close enough at some level. Why does it have to be, or is there any requirement for it to be an absolute threshold instead of signal to noise or something?
Yeah, so the threshold, so yeah, first to create a single recurrence plot like this, where it's just ones and zeros, you have to choose a specific threshold. But actually, I think it's in these examples. Here, the threshold is removed, and instead it's replaced with, instead of ones and zeros, you have just the distances between every pair of points, and that gets assigned a color, or a color map is introduced. So there, for a fixed threshold, yeah, it's harder to choose what's the right, what's the right threshold to choose.
No, I mean, why not use something like a signal to noise?
You could use
if something is within.
Yeah. So the kind of the rule of thumb with producing a recurrence plot, just like here, is to use the signal to noise as a measure, or the standard deviation, or the observational noise. So you would want the threshold to be like 5 times the size of the observational noise, so that you're not showing points that just happen to be close to each other due to noise, but are truly close to each other in phase space. So you want the threshold large enough to consider that. Yeah, and the methods I have used, actually, if you were to create like 100 recurrence plots, one for a different threshold over a broad range. So like what we would call the recurrence rate in each of these is basically how like dense is the entire thing. How many positions are filled in the recurrence matrix. So like the number of black dots versus the total size of the matrix is the recurrence rate. So you can do it from like 0% or 1% up to 99%. And there's going to, for dynamical systems at least, or ones that have something, something that has like QPO or something in it, or something that has not just noise, there will be a range of thresholds for which you will get a lot of quantities, like invariant quantities. And I can go into that more, but that's one method for like asking the question, are these features that I'm seeing, are those real? And what you would do is choose a range of thresholds, and you would want for a range of thresholds for there to be kind of a consistent result. So that's kind of how you handle noise or inherent noise in the system as well. So those quantities I'm talking about, there's actually 16 different quantities you can get out of the recurrence plot. Feel free to, if I'm like talking too much, please let me know. So there are quantities that you can get out of this. So determinism, for example, it's okay. I'm putting that in air quotes. Determinism. That's one of the quantities, which is basically how many points or black dots are part of diagonal lines versus the entire size of their recurrence plot, or versus the number that are just isolated points. That's quote determinism. That's one example. The longest diagonal line, which would be this like kind of long thing for the sinusoidal, is, if you were to take the inverse of that, that's related, not exactly, but that's related to the largest Lyapunov exponent, which is a distinguishing factor in nonlinear dynamics between systems. So there, in general, though, the diagonal features tell us something about determinism, periodicity. Vertically shaped features are things like time invariance, state changes. And this kind of checkerboard feature that's showing up with Duffing is because it's quasi-periodic. There's a driving term in the differential equation that shows up. So any kind of recurrence plot that has these kind of checkerboard features usually has some kind of quasi-periodicity in it. Okay, so applications. Oh, I think I might. I'm a little worried about time, so I might skip that, but I'll come back to, or I'll go over it quickly. One way.
I would say don't worry about the time.
Okay.
you know, we are used to people running over time. So it's
okay. I'll briefly cover this then. I use the surrogate data method. It's something that's used in the nonlinear community for distinguishing between stochastic and deterministic systems. So it's a data-driven null hypothesis testing. Basically, what you do in practice is you take your light curve. There's the hypothesis that the light curve is generated by, or is well described by correlated noise. So to test that, I would take the Fourier transform of my light curve, randomize the phases, and then do an inverse Fourier transform to obtain what I would call a surrogate. And if I do that like 100 times, so I get 100 different surrogates, and then I can perform some statistical test on my data, the original light curve and my surrogates. And if the data is significantly different than from the ensemble of surrogates, and we say, okay, correlated noise is probably not a good hypothesis or model for this light curve. That's a simplistic, you know, basically the ensemble of surrogates in this case preserve the power spectrum, but all the dynamical information was destroyed when we randomized the phases. And so basically we're saying the power spectrum doesn't describe all of the variability or that is contained in the light curve if they're different. You're going to do the same. There's a variety of different types of surrogates that you can produce. They all are different hypotheses. So one is the same flux distribution. That doesn't necessarily mean Gaussian. That just means that the flux distribution is the same, which can have a weird shape. Or I put in parentheses there, IAAFT. That preserves both the flux and the power spectrum. And that means iterative amplitude adjusted Fourier transform. I'm not going to say that. I'll just say IAFT. But that's how we would get, okay, let's take a recurrence plot of a bunch of surrogates and the data, calculate a quantity from the recurrence plot, such as what's the longest diagonal line, and see if they're distinctly different between the data and the set of surrogates. So that's the method I use. This is just what this looks like. HER-X1 has a 35-day clock, and these are 3 different types of surrogates that you can generate. And so I'm just going to show an application of this. I think this is the last thing I have. But I've been looking at the switch bad AGN, which this is all from the 70-month catalog. So 70 months of data, and I binned it to every 5 days, which was done in some other studies of the same catalog. And I looked at 46 AGN in the hard X-ray. So that's 14 to 150 keV. I ignored the highest energy. And there was another study by Shimizu and Mushatsky in 2013 where they found that all of these, for the same set of AGN, the same 40-ish ADN, the power spectrum slope was the same basically for all of them. It was -0.8 for all but one, all but one source. Oh, I see a stray little label here. And so that I thought this would be a great test for whether recurrence plots can uncover more than what's seen in the power spectrum. So this is what the recurrence plots look like for the sample. The kind of patchiness that's going on here, I think, is really due to the noisiness of these systems. But despite that, you do still see some structure, especially a NGC 4151 and SENE have some kind of dramatic changes in the texture, the patterns. And that's indicating to me that they're probably very non-stationary, or even maybe a state change of some kind is going on here. But you also see hints of kind of diagonal structure going on as well. So diagonal structures would be things that are like repeating behavior. Again, and then these large scale inhomogeneities are non-stationarity basically. So I generated surrogates for every one of these light curves, calculated recurrence plots of all of them, and then to quantify the structure, I looked at 3 quantities. which I've listed here. The longest diagonal line is a good tracer for nonlinearity or non-stationarity. Determinism traces is a good measure for actual determinism. And for stochastic behavior, I looked at the Shannon entropy, which is a measure of the randomness in the distribution of the recurrences. And I compared these to all of the surrogates for each light curve. Then it's okay, are there, on the one hand, is there significance against the surrogates generally? Because that tells us there's extra information in these light curves than we can see from traditional time series analysis. But on the other hand, the second question was, are there differences based on physical properties like type 1 or type 2 AGN, for example? So for type 1 and type 2 AGN, this is like super nominal, so I'm aware of that. But the thing I would point out is it does seem like there might be more so here I'm saying the longest diagonal line traces nonlinear behavior. It seems to be more a thing for type 1 AGN, especially if we include blazars, which is the smaller p-value here. But that's marginal at best. And but something I would point out is that is like 40% of high significance against the surrogates. So regardless of whether there is a difference between type 1 and type 2 AGN, there is a lot of differentiation between the light curves and their surrogates based on the recurrence plot. And I would highlight this is all based on the recurrence plot, so this is definitely, we would have to do further analyses to see if this is consistent with other types of analysis. But that is kind of an initial takeaway. This is ongoing work. I did the same, if we looked at radio loud versus radio quiet AGN, the radio loud, I mean, a lot of them have really high significance against their surrogates, but more so it seems like when there's a jet, when we're looking at the determinism, not necessarily nonlinearity. But a couple of the things I would point out with this is that if we're detecting nonlinearity, that doesn't necessarily mean like chaos or something. It could just be that these light curves are non-stationary, which I think is likely the reason for this.
Sorry, yeah. Rebecca, can you go back? So what you exactly plot? What do you plot on this figure? Because I just got lost. Yeah, exactly what is
what's
shown.
Going on. Okay.
Yeah.
So for each of these recurrence plots, for each source, I generate a recurrence plot and for the surrogates. And I compute something like the longest diagonal line. And I do that for the surrogates and for the data. Then it's a question, and I did this as a function of threshold. That's an aside. We were just talking about the threshold, but as an aside. To see whether there's high significance versus the surrogates for the longest diagonal line, for example, Lmax, I'll say. And so if the data is separated from the ensemble of surrogates, you can do something like what's the standard deviation range of Lmax for the surrogates, and if it's like outside like 3 sigma or something. In this case, for significance, I used a rank order test. But if Lmax is distinctly different than the sorry, I lost the figure there. Then the surrogates, then whatever that significance is. So here Lmax, and this is say with regard to the IAFT surrogates, so ones that preserve both the flux distribution and the power spectrum. For type 1 AGN, this is the fractional occurrence. So this is so that I can scale them to each other because there weren't exactly the same number of type 1 and type 2 AGN in this sample, but it was almost evenly split. So 40% of the type 1 AGN had high significance against their surrogates based on the Lmax measure. And then in the range that's like marginal to not significant, there's like half and then not at all significant, like almost the same, there's like 15% or so. And then the same with the type 2. And here I've just done a statistical test to see whether these distributions are the same, the Mann-Whitney test, to see whether is there a slight deviation. And this is a small number of statistics. That's why I'm not trying to claim anything huge here. There's certainly it's an open question, because this isn't a hard X-ray. The variability is predominantly occurring above 10 keV, which means that there should be no influence from obscuration or for these AGN. And so, but these objects are classified as type 1 or type 2 from optical spectroscopy. And so it is curious that has an possible effect on the results. So is there something in either this is a null result and I just happen to get a slight deviation, or there's something in the way that we classify type 1 and type AGN that has some kind of bias, or there is an association with the mechanisms that are associated with type 1 or type 2 that's related to the hard X-ray, which is really, close in coronal region.
Yeah, but my question was really to the plot and to your statistical evaluation of this significance. So compared to simulated light curves in some ways.
I think the more important result here, I mean, it would be really great if we could compare to physical properties. So I will say that this was with the 70-month catalog. I'm redoing all of this analysis on the 157-month catalog. So that will really put to bed whether this is a real effect or not. Because if it doesn't hold up with twice as long light curves, I would be inclined to say that's, this is happenstance. But the bigger point really is that these features that there's a lot going on in the recurrence plot that's not detected from like Fourier analysis.
Yes.
That's the bigger takeaway, I would say here. So, with the Swift bad AGN, this is kind of like my summary slide. It's nominal results when comparing to physical characteristics, but there is strong evidence that there's a lot of non-stationary behavior. So I am applying this to 157-month catalog. We'll see what happens. It's been a little slower than anticipated with COVID, but that should be out the door soon. And then some other applications. I have extra slides too, if you wanted to talk about the X-ray binaries analysis that I have going on. But basically, you can do the recurrence plot in a sliding window across the light curve and see if there's changes in the variability and see if that lines up with changes in the spectra, the energy spectra, I mean. So that's another project I have going right now with this kind of analysis. And then I've been putting together a Python package that's kind of has everything that we've seen here in this presentation, with like doing a time delay method, generating recurrence plots, generating surrogates, putting that together in a Python package. I have like kind of the bare bones on my GitHub right now. But I would like to, I'm working on adding some treatment for irregularly spaced time series, because I'm highly interested in doing a lot of this on a ZTF light curves. That would certainly be different science, but I think there's possibility here that recurrence plots can be used. So the time delay method really requires evenly spaced time series. So that's like a big, I would say, challenge, ongoing challenge right now. We want to be able to do this with gappy data. So yeah, and so the general goal really is, trying to classify variable objects using these recurrence quantities versus, slope in the power spectrum, which clearly does not capture everything that's going on. Yeah, that's basically everything I've prepared today. I don't know if folks have some more questions.
Thank you.
There's a link here. I find it really fun. I can probably put it in the chat in a second, but I don't know if I can get up the chat window. How do I get there? But
the bottom of the,
Actually, it's probably at the top of sharing the screen.
Sometimes the sharing of the screen is a little wonky.
All right,
But this is a fun little tool that somebody made where you take song lyrics and generate a recurrence plot from them. I just want to give a shout out to this person because it's actually really fun. And I think it's a really great conceptual tool for understanding what the heck a recurrence plot is. And you can find me here, but I'm happy if there are any more questions. Oh, thank you for putting that in the chat. I'm happy to chat about any of this.
Yeah. Well, any more questions from anybody who's still online? We have a group.
Do you have a feeling how many data points you need for any of these things? Like,
yeah, I would say it certainly depends on like how noisy the systems are, but for something, I would say like rule of thumb, you need probably at least 100 observations. So the 70-month, where do we go? This analysis was done on the 70-month catalog, and I did 5-day binning. So certainly less than 1,000 data points, but that's still substantial, I would say. And these are for really noisy systems. But yeah, I think you could probably do that. You could get away with, if you were to do like an ensemble study, like a bunch of light curves and do this sort of thing, not just 40, I think less observations, so really 100 data points. I would say the number of observations is more important than, the number of observations might be more important than the sampling.
you think we should have at least as many observations as we have data points?
Oh, sorry, to be clear. So when I said observations, I meant number of data points for a single light curve. So the number of data points in your time series, I would say around 100, 1 to 200.
Thank you.
I was actually a little confused, continuing to be a little confused about this plot that you have.
This one?
Up there, yeah.
Okay.
What is the comparison that you're making? I mean, what is the,
So,
there's a null distribution and there is an alternative hypothesis.
Oh, so
what are the two?
The two distributions are type 1 and type 2, and I use a Mann-Whitney test to compare them.
I see. So, for example, so that is what you're showing is actually the distribution of the Lmax.
Yes.
For the two things. I see.
Yeah.
Okay. The bar plots are confusing.
Yeah, I'm sorry.
Okay, and the p-value refers to the difference in the type 1 versus type 2.
The p-value, that's probably where the confusion is too. So I didn't explain it, I'm sorry. The first 0.13 is if we exclude blazars. 0.07 is if we include blazars.
Okay.
So type 1 versus type 2 have like the difference in their, there's basically a p-value 0.13 indicating that there's very nominal difference in the distributions. If we include blazars with type 1s, then the difference in those distributions increases slightly.
That looks like it is mainly just a sample size effect.
Yeah, I think so. Yeah, again, this is a sort of analysis that can be done, but I would say these results are nominal at best.
I also have a question about the randomization, the null, the way that you generate the null distributions by phase randomization and flux randomization.
The surrogates, yeah.
So I was just trying to think of how that would work. For instance, if you have a sinusoid, how would you do a phase randomization of such a light curve? I mean, wouldn't you always get, and then when you do a flux randomization, it'll completely destroy the sinusoid, you won't get, so any kind of Lmax you would get would be
Exactly.
significant.
Well, that's, yeah, I mean, that's kind of, if we're talking about a sinusoid, I mean, that's the classic example of showing how the surrogates will be ridiculously nonsensical.
Right.
And that is the point, though. So certainly with a sine wave where it's just a single sine wave, the power spectrum is just that one term, really. So yeah, I would say that's not an yeah, I mean, that's not an appropriate use of it because it's obvious already, I would say. But once you start getting you know, additional terms, or you have broadband, when the power spectrum looks more broadband, that's when it becomes more relevant to use the surrogate data method, because you actually have more terms than the single period. So yeah, and with the flux distribution, like if you're randomly sampling the flux distribution to create a light curve, I mean, that's basically, if it was like a white noise process, you'd have like a Gaussian distribution. And if your light curve is also Gaussian and white noisy, then there should be no difference between the surrogates and the light curve. But if that's a bad assumption, if the, you know, a Gaussian distribution or white noise is a bad model for your data, then yeah, it should be nonsensical, to your point. So.
So looking at your current images
Thomas,
here.
I think had a question. Oh, sorry.
Oh, Thomas, okay. Go ahead, Thomas. Oh, no, I was just looking at these images, right? So we have 9 different images, and I was wondering if there is a way to say that, let's see, NGC 4388 behavior, the variability behavior is similar to NGC 2110 or not. Like when you compare these recurrence plots, I mean,
you can compare the two. I mean, that's what the light curves are just like, you can't even see what's going on. And they just look like noise. And the recurrence plot somewhat as well, though I would say NGC 2110, you know, there's some kind of non-stationarity that makes this patchier. But yeah, I mean, it's very difficult with these kinds of systems to kind of categorize them by eye, which is why we would rely on these quantities like what's the average diagonal line length or something.
Yeah.
So you.
Well, I was just thinking about all this, you know, the machine learning methodology where you have, you know, comparing the images, right? So you have several of those, and you know, trying to look at the many of this and classify.
That is the application that I'm working. So my other hat at UW is a data science fellowship, and so I'm really trying to pair this analysis with machine learning, because I think using, even if we were to look at all 16 quantities that you can get out of the recurrence plot, you basically have 16 length vectors for a bunch of objects, and you can do clustering of those quantities, or using like dimension reduction or something. So yeah, that is, I think that's or even image recognition, like comparing these literally as images. Yeah, those are the techniques I'm exploring with this, because I think certainly a machine would be better at differentiating these than we are by eye, but that's the at least when it's this noisy.
So the SUNE and NGC 4151 in this here, they both kind of look similar to the Brownian motion plot that you had before. So is that a fair conclusion to draw, that the light curves here are better described as Brownian motion?
Yeah, actually, I think these are two of the light curves that, I'm doing this off the top of my head, but I'm pretty sure SUNE and 4151 are indistinguishable from the IAFT surrogates, which would be consistent with them being some kind of like heavily stochastic process like Brownian motion.
Right. Thomas had a question.
Actually, my question's related to what you asked, Anita. So, okay. Firstly, the 16 features that you use, sorry, I missed some of them. My daughter came in earlier to distract me. Were they like based on some scientific reasoning to use those features, or is something that is easy to extract from the images that you show here?
Yeah,
I'm just curious.
Yeah, some of them do have been. So the ones I chose here, some of them have been shown to be related to like actual dynamical features. So like if we were to study the recurrence plots of like known systems, like known differential equations or something like that, it has been found that Lmax is related to the entropy of, not Shannon entropy, a different topological entropy, which is a measure in chaos theory. But determinism tends to trace pretty strongly with actually deterministic systems, because something that's repeating itself on some time scale is going to have a high determinism measure from the recurrence plot. And then Shannon entropy as well. And those are 3 of the 16. Some of the quantities, some of the others are kind of redundant with these 3. So that's why I chose these ones specifically. Yeah. So. Yeah,
and other comments I have when I look at those the recurrence plots, they are basically like well, I would see them as binary images, right? It's black and white. Now my background is statisticians. I work with image analysis. So when I look at it, it just strikes me like one possible like model that we use to model images like that is a cellular automata. If you do it well, you may be able to extract something very interesting from it.
Yeah.
I don't know, okay, but it just strikes me that yeah, they look, how to say, beautiful, I should say, okay.
Yeah. I mean, I agree with you.
I like it. Yeah, they look beautiful.
These ones especially. I think when you get to, there are a lot of systems out there that have like classic, like very distinct behavior, such as some of these X-ray binaries, or variable stars even, or Cepheid variables, like that have very distinct light curves. And you can really use those as proxies for like, you know, if you're thinking of like a parameter space of what are all the different recurrence structures that you can see in the cosmos, you know, different classes of systems probably live in different areas of that parameter space, recurrence properties. So yeah, I mean, I think there's a lot of promise here for classification for that reason.
Yeah, you just, how to say, yeah, find there are many ways to do classification. It's just cellular automata, I think, would be interesting way of, well, one possible way of modeling what you have there is.
Yeah.
So one more question. When you were talking about these plots, which are displayed now, you said that this, you know, LMCX3 has this sort of diagonal lines which are not really diagonal. It's the curve. I mean, because when I look at it, it looks like they are all diagonal.
Yeah.
But there are some which are not. So how do you evaluate that they are not diagonal? Do you do some analysis on those?
Yeah, I would say, so this is where, like, actually I have some extra plots. Let me see. The way I do it is, okay, so this is like a huge change. I'm sorry. There are a couple recurrence plots you can get from Active Galaxies. Active Galaxies from Kepler, which have beautiful sampling. These are somewhat saturated just to show the differences in the patterns. But if you were to sum up along the diagonals, like collapse this along the diagonal so that you're summing each offset from the main diagonal into like a histogram, that's what's going on here on the right. You see, you start to see, oh, there's a lot of recurrences kind of like pretty consistently every 50-ish days for one of them. So that, and it's hard to see that in the recurrence plot itself, but you do see the traces at the repeater. So if I were to do this with LMCX3, we might kind of get this broad band. This is very similar to like an autocorrelation function. It's like the nonlinear version of it. It's sideways, but yeah. So like where I have this dotted or dashed line, it's basically sum all of the recurrence points along this dashed line. And you'll get this peak here at 52 days. And then you do it again, kind of where these checkerboard features are. That's about 50 days later at the second peak. The patchiness is just me comparing it to ensembles of surrogates anyways. So, but yeah, it's like an autocorrelation function. That's how I would try and distinguish diagonal features and see if, if this ends up being really smeared, like super smeared, then you would be like, okay, you can see diagonal features going on, but it's changing over time enough that you'll see kind of a mess in this what I call close returns. Yeah, that's one way to quantify. That's one way to get like timescales, I would say, is to do something like this close returns.
So this timescale which you plot here is just because this is like the correlation function kind of.
Yes, exactly. Yeah. So higher peaks means higher correlations.
Yeah.
In this case, that means more recurrence points for a specific threshold. So this was done for a specific threshold, but I could do it for every threshold, and I would see the same peaks at the same period. Yeah.
Interesting. This is a different way of looking at the variability. You have to adjust your mind to see the things. But yeah.
This is actually, I should mention, it's kind of similar to the delta intensity, delta time plots that Ashish Mahabal came up with a while ago. But he never went past the, as far as I know, the making of the plots to evaluating the significance. So this is very interesting.
Yeah, the darker purple is like high significance against surrogates, and the light purple is like within a two standard deviations, I think, of the surrogates. So definitely the 50-day timescales is substantial, is the takeaway here.
Looks nice.
Yeah. So anyways.
All right. Any other questions?
Thank you.
Thank you, Rebecca.
Yeah, of course.
Thank you. It was very nice. So as we said at the beginning, if people have questions, they can email you, I guess. So
yes, absolutely. Just shoot me an email or, hit me on Twitter.
Yeah, it's a lot to digest right now.
Yeah, I understand.
Thank you very much.
Yeah. What was that?